I believe, about representation learning, or you can think of it that way. So Kevin got his PhD about a year ago with Josh Tannenbaum and Armando Solar-Lezama at MIT. He will be an assistant professor at Cornell, or already is, but he's spending some time in a small company. And Kevin, with that, thank you for joining us. We look forward to your talk.
Sure. Thanks, Russ. Let me just screen share. Or can people hear me?
Yeah, it's great to hear you and see everything.
Okay. All right. So yeah, thanks for organizing this symposium series, and I'll be talking about a system called DreamCoder, which I built over the past few years with my collaborators, mainly Kathy Wong, Max Nye, Matthias Lomayer, Lucas Morales, and my advisors, Armando and Josh. So I'm going to be talking about a kind of program synthesis called program induction, which is really a way of thinking about knowledge representation for AI systems. And the way you should think of it is that we want to build AI systems that represent their knowledge as programs, as symbolic code. And a consequence of that commitment is that if we're going to be doing any kind of learning, if we're going to be adding to that body of knowledge, then that means that we're going to be making new programs or doing program synthesis. So from an AI point of view, there's a few reasons why you would want to do program induction. One of those reasons is that programs tend to generalize pretty strongly. Like that's kind of what it means to be an algorithm, that you can like run it on new inputs and it'll keep on doing the same thing. And because you can often like learn, because these programs tend to extrapolate rather than interpolate, it means you can often learn them from much less data. Not all programs are interpretable, as I'll be discussing in this talk, but programs in general tend to be more interpretable than other representations. For example, contrast a programmatic representation of a 3D object like a drill in a CAD engine, which has like parts that you can pull apart and edit and things like that, with the analogous point cloud or mesh representation, like what I've shown on the bottom. The program representation, the CAD routine, is way easier to recombine and recompose in all sorts of new ways than the corresponding mesh representation. But really the most celebrated feature of programs is the fact that they are Turing complete, that they're universally expressive. And that means that, at least in theory, like in principle, they have the expressive power to capture the kinds of things that are solved by intelligence. So there's been a lot of successful systems which have been built which induce programs. So of course, the most famous one that most of you are probably familiar with is this Flashwell system. But because programs are universal and you just got to kind of change the programming language to adapt to a new domain, there's been other systems, for example, this system called Zelensky, which can synthesize these intricate 3D CAD routines, which have like loops and things like that. And underneath the hood for all of these systems is some kind of domain-specific language, which imparts like crucial prior knowledge about what the kinds of programs are going to look like that are successful in this domain. And in practice, if you want to get one of these programming systems off the ground, you need to have a good domain-specific language, as well as usually a custom synthesis algorithm that operates over that language. So even if you look just at like graphics programs, so all these systems infer some kind of geometric or graphics program from perceptual data, all the programming languages have a lot of similarities, but there's also key differences. So I think that the kind of challenge that this poses to us as AI researchers is how can we make learning systems which can adapt the programming language that they're operating over in order to tune themselves to some new domain. So I think of this as like a kind of learning to learn, because you're learning to do program induction and you're using program induction to do learning. And from that viewpoint, if our goal is really acquiring the domain-specific knowledge in order to induce some new class of programs, that means we have to learn something about the DSL. We need to learn, concretely here, we're going to learn like a library. So a library of abstractions or subroutines. But also we need to learn how to deploy that library at test time in order to solve new problems. So this is like a inference strategy or like a synthesis algorithm. So we have a system which learns both these things jointly, and I'm going to illustrate how it learns a library for doing list manipulations in a very simple setting. So really imagine that you wanted to induce a program which sorts a list of numbers. So you might give a specification in terms of input outputs, such as those shown on the right. And you might initially give to the system some generic but fairly Spartan set of components which you can use to synthesize. So things like conditionals and map and fold and stuff like that. So somehow we got to bridge the gap from the components on the left, this initial library, to a program which can solve the problem on the right. Now the system which solves this problem doesn't look at just a single synthesis task in isolation. It's not just looking at sorting lists of numbers, it's also looking at around 100 other problems, some of which are easy, some of which are hard. And it starts out trying to solve these problems, and as it solves some of the easier ones, it then uses those to build out a library of higher level routines, which we hope will eventually allow us to sort lists of numbers. So for example, after this algorithm has run for a little while, it defines a new procedure in its library. Here it was the fourth procedure that it defined, so I've called it concept 4. And concept 4 relies, for example, upon the fold function, which was built into the initial primitives. And concept 4 is really the higher order function filter. So it takes a predicate and a list and filters out all the elements of that list which do not satisfy that predicate. So filter is a nice function to have, but it's not in and of itself like going to get you really far toward a sorting algorithm. Now, if you run this learning algorithm longer, then what you see later is that the 13th function that it decides to add to its library is a routine that builds on filter and which computes the maximum element of a list. Now, this is almost all the way to sorting. Like computing the max is very useful for sorting. And if you go deeper into its learned library, one of the final routines that it learns calculates the nth largest element of a list. And once you have this routine, it's very easy to express a solution to this sort list problem. All you have to do is repeatedly call concept 15. You just have to say, get the first largest element and the second largest element and the third and so on. And then you've sorted your list. So the solution that it eventually finds is very compact and interpretable and does not take very long for the synthesizer to discover. But in principle, it would have been possible to solve this problem without this library learning. So in particular, you could have expressed the program that it found in terms of the initial primitives that we gave to the system. But this program is extremely long and hard to understand. On the surface, it kind of doesn't obviously have anything to do with sorting. You'd have to stare at it for a really long time to figure that out. And it's not just obfuscated. There's also like a deep sense of which it's like inaccessible. Like there's no reasonably bounded search that could like ever discover a program this long. Certainly, I don't know. You certainly can do this with like a brute force search. So in particular, the program that we found, the short one in terms of concept 15, the synthesizer can find in under 10 minutes. But if you wanted to do brute force search and try to find this lengthy program, it would take far longer than the age of the universe. So now what I'm going to do is I'm going to explain the algorithm which built this library and which wrote the code which solved this list sorting task. So this algorithm is called DreamCoder, and the reason why it has this name is because its structure and its mathematical framing is based on wake-sleep algorithms, which are unsupervised methods for training neural networks, the most famous of which is probably the Helmholtz machine. So inspired by wake-sleep algorithms, we have something which is called a waking phase, which corresponds to running a synthesizer. And we have a pair of interleaved sleep phases. So in what I'm going to call abstraction sleep, we are going to improve the library. So we're going to add new functions, just like I was showing you earlier, where it's defining like filter and compute maximum. And then we're going to have another sleep phase, which trains a neural network called a recognition model to help guide the search over programs that occurs during the synthesis phase or the waking phase. So from a kind of Bayesian point of view, what's really going on here is we observe a bunch of synthesis tasks, and I've shaded the tasks to mean that we observe them. So we get to see some specifications, and we have to infer a program that solves each of those specifications. These programs are unshaded, which means that we don't get to see them. And at the highest level, we also need to infer a library which kind of unites all these programs and says, here are the kinds of components which are useful for writing programs that solve tasks that look like this. So just to kind of foreshadow the approach, one way that you could imagine doing inference in this model is to just kind of fix some library. So pretend that you observe the library, just fix it, and then say, okay, now I want to infer the best programs given that library. And then if you had some way of inducing libraries, you could pop back up and say, now I want to infer a new library. And you could sort of alternate this process and eventually iterate until some convergence point. So one twist that we're going to add here is we're going to train a neural network, which, as I said, is called the recognition model, which is going to learn to map from a specification to a probability distribution over the space of all programs, and will assign more probability mass to programs that it thinks are likely to solve that task. So by training the neural network, we're going to effectively guide the synthesizer, and we're going to be kind of amortizing the cost of performing synthesis. So we sort of pay a cost for training the neural net, and then that cost ends up becoming amortized in the process of solving many synthesis tasks. So this is the kind of Bayesian perspective on how DreamCoder operates. Now, if you look at this picture here, which I'm just going to put here on this new slide, there's really three things we don't know. We don't know the programs, we don't know the library, and we don't know the neural network weights. And because there are three things we don't know, that motivates a three-step iterative learning procedure where we hold two of those things fixed and then solve for the other one. So this iterative learning procedure corresponds to the wake, abstraction, and dreaming phases of this algorithm. So during the waking phase, or the synthesis phase, what we do is we take a task. So for example, input outputs from some specification, and we have some current library, and we pass that task to the recognition model, which outputs a distribution over programs which biases a search over the space of ways you could combine components from that library. And we search until we either hit a timeout or until we find enough solutions to that task. During the dreaming phase of sleep, we're going to train our neural network, our recognition model. Now, the recognition model maps from programs to tasks, so it has to be trained on pairs of programs and tasks. But we're assuming that we don't actually get to see any ground truth programs. So we need to, in a self-supervised way, get some programs as training data. So the simplest thing we could do, and here on the slide what is marked as replays, is to simply take programs that we found during waking and take the task that they solved and teach the neural network that when it sees that task that it solved, it should predict the program which solved it. So the problem with this, though, is that in practice, we're often running the system on only maybe 50 or 150 different tasks, and that's not really enough examples to train a high-capacity neural network. So another source of training data is to take our library and just randomly assemble components until we get a program, and then run that program to see what it does. And so the advantage of this is that we can make as many random programs as we want. So we have unlimited training data. But the disadvantage is that random programs in general are not going to be representative of the kinds of programs you actually want to write. But as I'll show, once the library has changed itself so that it matches the distribution of programs that solve tasks in the domain, these so-called fantasies or random programs end up looking a lot like the actual training data. So it's like a kind of domain randomization or data augmentation. During the abstraction phase of sleep, we replay programs that we found during waking, and we refactor them in order to extract reused parts of their syntax trees. So you can think of this as a kind of compression where we're trying to compress out reused syntactic patterns. So I want to talk briefly about each of these sleep phases. So in the abstraction phase of sleep, which you can think of as like learning parts of a DSL, in particular, learning a library of components, it works as follows. So imagine we had two tasks specified as input outputs. On the left, I'm showing you a task, which is take a list of numbers and double each element. And on the right is a task, which is take a list of numbers and decrement each element. So during the waking phase, we could solve each of these tasks. But imagine that we don't have the higher order function map. Instead, we just have recursion implemented via the Y Combinator. So with enough compute, you can still solve these problems. But the code you get out is hard to find because it's long. And it's hard to look at these things and see what they're doing because they're very long programs. So during the abstraction phase of sleep, what we do is we pass these programs to an algorithm which builds a data structure that represents a very large set of possible ways of refactoring them. In this case, it ends up considering on the order of 10 to the 14 such refactorings, and I've highlighted in each of these boxes one refactoring of those 10 to the 14 for each of those programs. The part that I've shaded in orange is a subtree that these two refactorings have in common. And if you were to yank out that subtree and add it to the library, then all of a sudden, these programs jointly would be much easier to write down. So we get more joint compression if we added this orange subtree to our library. The orange subtree corresponds to the higher order function map. So in this case, what's going on is we gave it these two initial tasks. It didn't have map. It did a bunch of search to find programs in terms of the Y Combinator. And then during the abstraction phase of sleep, it pulled out some common expressions that these two things could be refactored into. And in the process, defined map in its library, which could then be used in subsequent wake cycles to solve harder tasks. So 10 to the 14 is a terrifying number, but we don't actually consider that many refactorings. The key insight is that most of these refactorings actually share a ton of common structure. And you can build a data structure which combines ideas from equivalence graphs and version space algebras, which exploits that massive sharing and which allows these kinds of refactorings to be performed tractably. So I'll now talk about the neural network and the ways in which it's trained during the dreaming phase of sleep. So remember that it's trained on fantasies and replays. So we're just going to be focusing on this part of the system here. So the neural network takes a task, and you can think of it as outputting a program that solves that task, but really a better way of thinking of it is it takes a task and outputs a distribution over programs, and you could then draw samples from that distribution. So this kind of high-level setup is something that lots of folks in the PL/ML community have thought about. So, and there's many different choices for what the neural network could be. So for example, it could be an autoregressive recurrent neural network, such as the robust fill system. It could be like a unigram model, which just predicts the probability independent of all other components in the program of using any one component. So for example, DeepCoder did something very similar to the unigram model, and this work by Menon and Gowani very explicitly like trained a unigram model. So what we ended up finding empirically is that something that is kind of a happy medium that works well here is a bigram model over syntax trees. And this is a probability distribution which predicts the probability of a child node conditioned on its parent and which argument of that parent it is. So this is like a bigram because a bigram conditions on the immediate successor in a sequence. And here is like a distribution over syntax trees which conditions on the immediate ancestor in the syntax tree. So child conditions only on parent. In a bigram, the next token conditions only on the preceding token. So concretely, imagine that we have some program where at the root we have a plus sign. Then this bigram distribution predicts a probability of what its left child should be, given that it's a plus sign. And maybe it predicts that it should almost certainly be the number 9. It also predicts what the right child should probably be. and here it decides to multiply. And then you can sort of recursively unroll this at each time, conditioning only on the immediate parent in the syntax tree. So there's a couple of reasons why we do this. One is that similar to DeepCoder, we only have to run our neural network once because we're just trying to get a bigram transition matrix. So that means that our synthesizer is bottlenecked not by how quickly we can run our neural net or by how fast our GPU is, but instead by how many CPUs we have. So we can then build a parallel synthesizer which parallelizes over CPUs. The other advantage is that you can learn to break a lot of syntactic symmetries. For example, you can learn to not multiply by 1 by simply zeroing out the probability of generating a 1, given that your parent node is a multiplication symbol. So now I'm going to talk about how these two sleep phases interact in a few different experimental domains. So in the paper on arXiv that I've cited at the bottom, we apply this to a range of domains, but I'm going to zoom in here on some planning and inverse graphics domains, a recursive programming domain, and an equation discovery domain. So for the inverse graphics domain, what we do is we give the system a corpus of logo or turtle graphics images, and we give it a programming language which has control over a pen, and it can also calculate like angles and distances. And its job is to draw each of these pictures by writing a single program for each picture. Now, if you run this algorithm on this data set, what happens is as follows. So on the left, I'm showing the initial logo graphics language given to the system. On the right, I'm showing a few sample images that it had to draw, and beneath each of them, the code it wrote to draw it. And in the middle, I'm showing the library that it learned in order to draw these kinds of pictures. So for instance, when it's trying to learn to draw this swirly beach ball thing, what it does is it calls out to learned function 8 and learned function 4. Now, if you look at learned function 4, it is a parametric drawing routine which generates spirals. And if you look at learned function 8, it's a higher order function which takes another drawing routine and repeatedly runs it while spinning around in a circle. So this makes a lot of sense because if you look at this swirly beach ball thing, it kind of looks like a spiral that's been like spun around in a circle. So function 8, I think, is kind of interesting because it's really a higher order function, and it corresponds to the geometric concept of radial symmetry. So rather than bake in these kinds of symmetry operators, as long as you have higher order functions, you can, in principle, like learn these things inside of the library. If you look at other routines in this library, some of them are very interpretable and kind of unsurprising. There are things like routines for drawing circles and polygons. But other routines are a little weirder and harder to interpret, like this parametric arc drawing routine. So the arc drawing routine, I don't really have an English word for it, but the system nonetheless finds it like useful for explaining many of the images that it has to draw. Now, this library that it's learning is kind of like a representation of its symbolic knowledge of the domain. So it's like a vocabulary that's assembled for expressing solutions to these drawing problems. But at the same time that it's growing out this vocabulary, it's also learning statistical knowledge that allows it to map between problems and probability distributions. And that statistical knowledge is embedded in the weights of a neural network. It's really helpful to also look at how that neural network is growing over time, and in particular, how its training data is changing over time. So recall that the neural network is trained on fantasies or randomly assembled programs. So at the initial point of learning, these fantasies we expect to be very simple and unstructured. So here are what these dream programs look like prior to learning a library. So here I've color-coded each of these images to show how the system drew it, starting with dark blue and ending in light pink. And most of these random programs are relatively simple and unstructured. These would not be good training data for a neural network. So actually, these are sort of the most interesting examples from 150 draws, because most random programs before learning are just single line segments. So now we should look at what random programs look like after learning. So after it's built that library. So after learning, what you see is a kind of recombination or remixing of latent subroutines that were in the data and which it inferred were good ways of explaining the images that it was seeing. Now, you might notice that these images look more complex in the training data, and that's because for fair comparison with the previous slide, these are, again, the most interesting dreams from 150 samples. But you should think to yourself, what do you want to train your program synthesizer on? Do you want to train it on data that looks like this, or do you want to train it on data that looks like this? So once it's learned its library, that kind of bootstraps the training data for the neural network. So we can also train it not to draw pictures by moving a pen over a canvas, but also to build towers by moving a hand in a kind of Tetris-like world. So here we give it these construction problems. And if you look at its learned library, you see kind of like higher order like planning macros. So these are kind of like options, but they're parametric. And again, we can look at the dreams before learning, and we can look at the dreams after learning. And again, what you see is that learning this library gives better training data for the neural network. So it's also helpful to look at the system's learning trajectory over successive wake-sleep cycles. So at the initial point of learning, almost no problems are solvable. Only the easiest problems can be solved. But then over successive wake-sleep cycles, the system is able to solve more problems, learn a better library, train a better neural network, use that to solve more problems, and so on. And so you get this kind of bootstrapping action. Now you might be thinking, do we really need both of these sleep phases? But if you ablate either of them, interestingly, you still get the same bootstrapping action. You just get much lower asymptotic performance. We can also compare with a range of baselines. So I think that the most interesting baseline here is the enumeration baseline, which asks, what would happen if you did a huge amount of search without any learning whatsoever? So in particular, what if you just ran an enumerative synthesizer for 24 hours per problem? Here we are running it for 10 minutes per problem. And what you see is that even with more search, like you still need learning in order to get the ball rolling. And if you look across many different domains, the same kind of global picture emerges, that learning unfolds in a kind of bootstrapping way over multiple wake-sleep cycles, and that you really do need both of these sleep phases in order to get to the highest level of asymptotic performance. So I think that the reason why each of these sleep phases does better, or why you need both of them and not just one of them, can be explained very intuitively. And it's by thinking about these three phases of the algorithm as follows. So during waking, we're kind of doing like problem solving or synthesis. And as we solve more problems, as we successfully synthesize more solutions, we then have more training data for the library. But as you saw in the pre and post learning examples for the dreams, a better library gives better training data for the recognition model for the neural network. But the recognition model is being used to guide the combinatorial search over all programs. So a better recognition model means that you can solve more problems during waking. So you get this kind of virtuous cycle where when one part of the system improves, it kind of echoes and reverberates throughout the rest of the system, and that sort of causes them to interact synergistically. So this story is, I think, fairly intuitive, and there's also some empirical data to back it up. That empirical data comes from looking at the evolution of the library structure over the system's learning trajectory. So here what I'm plotting on the x-axis is a statistic of the library structure, namely its depth when viewed as a network. And on the y-axis, I'm plotting how many problems the system can solve when it has that library. In darker shade, I'm showing what's going on early in training, and in brighter shade, I'm showing what's going on later in learning. So as the system learns more, as it goes through more of these cycles, the libraries get deeper, and also the libraries tend to solve more problems. Now, here's what happens if you ablate the neural network. So if you get rid of the dream phase of sleep. So as you can see, two things happen. One is that the neural networks the libraries become more shallow, And also for a given library depth, you still solve fewer problems. So by having the neural network, we both get better libraries because we get deeper libraries, and those are correlated with performance. But also for a given library depth, there's an extra bump to performance from the neural network. So adding the neural network improves the libraries that you get. And analogous but weaker trends hold if you look at a different statistic of the library structure, in particular its size. So in what I've talked about so far, we built in a what was still like a very custom domain-specific language, like a language for logographics or a language for moving a hand around in a Tetris-like world. But in principle, we should be able to start with a more generic kind of programming language and then use the exact same algorithm in order to enrich it and move it closer to something that looks like a domain-specific language. So I'm going to look at two case studies which explore this. One which starts with something like a modern functional programming language and then learns a language for vector algebra and physics. And then one which starts with a very basic kind of Lisp and then tries to learn something which looks like that modern functional language. So for physics, what we did is we took equations from AP Physics and MCAT cheat sheets, and we simulated random data. So we took each equation and ran it with random input outputs, and then got kind of like simulated data for each equation. And then we asked the system to come up with programs which can fit each of those simulated data sets. So here's a few example equations on the right, and on the left are the things that we initialize the system with. And crucially, you can see that it has some domain-specific stuff, like the number pi, but it also is missing some important things. For example, it has no knowledge of vectors, and instead, it just knows about lists of numbers. So we encode all vectors as lists of numbers, and we should expect to see that the system discovers that it's more compressive to define vector algebra routines. So indeed, that's roughly what we see in the sort of first layer of its learned library. We see basic vector algebra components like addition and subtraction of vectors. And as we go deeper into this library, we see that it can build on top of those routines in order to define things that look a little bit less like vector algebra and a little bit more like basic physics. So things like integrating second derivatives over time. And if you go into like the final layer of the library, you see stuff that is definitely physics and definitely not just vector algebra. Stuff like schemas for inverse square laws or templates for calculating the period of oscillators. So once it has this library, it can solve most of these cheat sheet physics problems. And usually the code it writes sort of maps intuitively onto how, like as a person, you might parse that equation. So for example, for Coulomb's law, it uses its inverse square law schema and composes that with its vector subtraction operation. But if you were to translate that into the initial primitives, then it would not in any obvious way have anything to do with Coulomb's law. It would just look like a mess of maps and folds. So by learning this library, these solutions became more interpretable and also search became more tractable. So here, instead of building in functional programming primitives, we wanted to learn them from a more generic and smaller basis. So in particular, we gave it things like cons, car, and cdr, and also crucially recursion via the Y Combinator. And we gave it like a problem set of around 24 or so functional programming exercises. So interestingly, in the very first layer of its learned library, the things that defined in its like first sleep cycle were these two functions. One of them is called fold, which recursively consumes a list, and one of them is called unfold, which recursively generates a list. So each of these can be defined in terms of the Y Combinator, and in a very precise technical sense, they kind of are like a basis set that spans the ways that you could operate recursively over lists. And once you have fold and unfold, you don't actually need the Y Combinator in order to do recursions over lists. And so it turns out that the system decides to never use the Y Combinator again, decides that that's like too cumbersome. and instead to build up routines on top of map and fold. So familiar things like map and filter, which are folds, and these sort of unfamiliar unfolds that it decides to define. Things like this routine I called count to and count down and unfold list, but also familiar unfolds. Like if you know range from Python, that's an example of an unfold. In addition to these kind of unconventional unfolds that decided to define this range routine, as well as things that bring together the fold and unfold families like indexing into a list. So the style of coding where instead of doing explicit recursion, you use these higher level operators, fold and unfold, is sometimes called origami programming. And I really like this exposition here by Jeremy Gibbons, although the idea itself is older than this citation here. And while it's interesting that it kind of retraced this style, I think that the broader point that's being illustrated is that you're kind of not stuck with the symbols that you start with. So here, I told it use the Y Combinator, but then it's possible for it to instead define other symbols on top of those and then proceed to ignore the Y Combinator for the rest of its execution. So this experiment took an unusual amount of compute because it was trying to bootstrap itself from a very minimal basis. In particular, this took approximately an entire year of CPU time. I don't think that you should actually run library learning algorithms for an entire year. This is more of a kind of sanity check to make sure that like the refactoring algorithm can handle higher order functions and things like that, and to show that in principle, these things can be learned from more basic starting points. So I think that actually you should build in things like map and fold because we know that these are generically useful for many different kinds of problems. So there's a couple different lessons that I think we can take away from this. One is that learning a library can interact synergistically with neural program synthesis. Each of them kind of bootstraps the other. The other is that programs are not necessarily interpretable. I mean, think of like assembly code versus Python code. But here what I'm arguing is that if we grow the language based on training data, then it can be both more friendly for synthesis, so it can make problems more tractable, and also it can make things more understandable for humans. The last lesson here is that you can maybe learn from scratch. Maybe you could, in theory, start with like combinatory logic or something like that and try to learn a library which could solve lots of things. But I think that'd be totally nuts and it would take tons of compute. And the nice thing about synthesis is that it makes it very convenient to build in the kinds of things that we know are good ideas and then learn on top of those things that we built in. So that's it. And I'd like to thank the organizers and my collaborators. And I'll take questions.
Thank you, Kevin, for the great talk. Please, I would like to encourage attendees to ask questions. It seems that Radu is ready.
Yeah, so very nice, very inspiring talk, Kevin. So the main idea is of the library is that you have the maximum amount of sharing among the code, yes?
Yeah.
So you can think of it as actually the set of capabilities, let's say, of an agent. So, and you can grow. Now, one interesting question is how in order to get to more tasks and more things, you have to give them more data, input data. Am I right? So how do you come up with that? So,
Yeah. So I think that what you want is something which covers like a wide range of difficulty levels and something which also makes up a consistent domain. So for example, if you had like very easy graph search problems and very difficult like image generation problems that clearly wouldn't work. For example, one thing like one of our domains, which I didn't discuss in the talk, was this generative regular expression domain, where we crawled a bunch of CSV files from the web. And this kind of naturally had like a spectrum of difficulty because some CSV files are very simple and small, like maybe they're just like monetary amounts, and others are more complicated, like they might be like addresses. And so the tasks here were to generate each of these CSV columns. And so you end up getting like a nice spectrum of difficulty. And also you get like a consistent domain because you tend to see like reuse of concepts across CSV columns. You know, like you might have like one column which is just years and like another column which is like the entire date. So you can like reuse the year concept in the like entire date concept. So you need something like that. One thing that I think would be interesting to explore and that we haven't explored would be to kind of look at like actual programming, like actual PL problem sets or something like that. Like get like real Lisp exercises. I think that, you know, that might not work quite as well because when human students are doing these problem sets, they also get a bunch of natural language that's informing how they think about it. It's not like they're learning all of this from input outputs. So one thing that Kathy Wong, one of my main collaborators on this, has been exploring is ways that you could augment this algorithm with natural language side information. So in addition to getting like input outputs, you would also get like a natural language description of what the task is supposed to be solving. And so, you know, I think that kind of something like that might help it work better in more human-like settings where you're not just learning from input outputs.
Mm-hmm. Thank you very much. Very, very interesting.
Do we have additional questions?
I have a question. How do you, so in your examples, the concepts that you're learning through this refactoring are very nicely interpretable. But I mean, how come they're interpretable? Is there kind of some reason behind? Because I could imagine that there would be other refactorings that would be less meaningful.
Yeah. So first, I should say that they're not all interpretable. You know, I would say like a little more than half are like very easy to interpret, but then there's a bunch of them which are useful for the synthesizer and also compressive, but where I definitely would not like intuit that this is like the right library routine. So like that arc, that weird like parametric arc thing in the drawing example is one instance of that. And the you know, the ones that I highlight in the talk, like, you know, like get the nth largest element of a list, tend to be like biased towards interpretability because I, you know, want to be able to show an example and people who say like, oh yes, I see, like it like makes sense. But there's, you know, I also want to show like the ones that don't work. So like I think that the reason why it's finding these like weird kind of esoteric looking routines sometimes is because when humans are thinking about how to carve up the world into concepts, like we're not just trying to find the most compressive representation. So for example, in the NumPy library, we can multiply matrices in several ways. We can take the transpose of a matrix in several ways. And any of that redundancy is actually coming at the expense of compression. So, you know, NumPy would be strictly more compressive if there was exactly one way to do every single operation. So whatever kind of inductive biases that we as human coders bring to the table, it's something which is more sophisticated than just compression.
Thanks. Yeah.
Kevin, one quick question. In your ablation study, you showed that the recognition model alone is more powerful than the abstractions alone, right? So if you had to pick one, you would just use that. Is there a reason for that? Is it perhaps a function of the algorithm that you use to then synthesize the programs?
I think it's actually just because bigrams ended up working a lot better than we expected. So earlier in the work that this builds on, which we called EC squared and published a couple of years ago, we did like a unigram model, and the neural network by itself was strictly inferior to library learning by itself. So I think that what happened is we just souped up the neural net more than we souped up the library learning. I don't think there's like a deep principle that like one of them has to be strictly better on its own than the other on its own.
So you don't think there is perhaps some fundamental thing like the neural model actually remembers the abstraction, sort of encodes the abstraction and sort of as a macro expansion, so to speak, produces that sort of expansion that the library learning captures in a new primitive?
Okay, actually, you're right. There is a deep thing at play here, which is the neural network in principle can encode everything that the library learning can encode, but the library learning in principle cannot encode everything that the neural network is doing. So that's not true for like our bigram model, but for something like a transformer or like a LSTM, in theory, the LSTM implicitly inside of its weights could just kind of like memorize these library routines.
And the bigram cannot do it because you really have just the context of the current node, right?
Right, yeah.
Right. But also conditioned by the example, right? Or not? Yeah.
Yeah.
It is. Okay. Yeah. Well, I hope we'll get to talk about it some more. Are there more questions? Fantastic 4 talks. I really want to thank all speakers for dedicating their time, everybody else for joining us. And thank you again. Have a nice day.
Thank you very much. Bye.
Thank you.
Bye. Thank you. Bye.